Okay, and we're back to go over the second part of this. Okay, so uh we did the first part, Boyles, Charles combined, and Gay-Lussac's. Now we're going to talk really quickly. This is not going to take too long. We're going to talk about Dalton's law of partial pressures, Graham's law of diffusion, and the ideal gas law. Where did I put that? Yeah, up there, ideal gas law. Okay, first of all, Dalton's law of partial pressures is a really, really simple one. It just states that the pressures are additive. Okay, so pressures are additive. If we have two gases, both at 4 atm, and then we take them and we put them into one container that was the same volume as the other two containers, their pressures are additive. It's that simple. You'll see it. It's much easier to see once you do some of the problems. Okay. It's also the total pressure is equal to all the pressures combined, all the pressures of each gas combined. Okay. The next law, Graham's law of effusion and diffusion. This one's a little bit trickier. Okay. Effusion is the escaping of a gas through a hole. So here, the effusion, if you have a hole, as the gases escape through that hole, that's called diffusion. Okay. Diffusion is the spreading out of gas into an area. So if we have a partition here and we remove the partition and now the gas spreads out, we call that diffusion. Okay. You can also think of it as someone sprays like cologne in the room and it spreads out, like someone sprays it in the back of the room. You can smell it in the front because the gas spreads out. Okay. Now the rates of these things are calculated both the same way. The rate of effusion for uh, gas 1 over the rate of effusion for gas 2 is equal to the square root of the molecular weight. So that's the molar mass of the second gas over the molar mass of the first gas. Notice these are switched. They're flipped. It's rate of effusion for 1 over 2, molar mass of 2 over molar mass of 1. Okay, so be really, really careful. So if you want to compare the rates of effusion for nitrogen and helium, you have rate of helium over rate of nitrogen. Then you have molecular weight or mass of nitrogen over helium. And it's the square root of those two things. Okay, so you do the math there, and then 2.7. So you know that helium diffuses 2.7 times faster than N2. Okay, smaller atoms or molecules effuse faster. So effuse or diffuse faster. Okay, so the smaller the molecule is, the faster it's going to effuse or diffuse. It's just going to move faster. Okay, and then the last one here is the ideal gas law. So this one incorporates all four variables: pressure, volume, number of moles, and temperature, and then has this value R. Okay, R is an ideal gas constant. Okay, the ideal gas constant is always 0.0821. Okay, and the units for that are liter ATM over Kelvin mole. Okay, pressure must be in ATM. Volume must be in liters. N is number of moles, that can't be anything else. And temperature must be in Kelvin. Okay, so let's do some problems. So ideal gas. So again, PV equals nRT. How many moles of gas, so we're solving for moles of gas, are contained in 890 milliliters? So volume is 890 milliliters. Our temperature is 21 Celsius. And our pressure is 750 mmHg. Okay. Now, those are our variables. We're looking for N. The first thing we always have to do is convert all of these things to the correct units. So actually, I'm going to move pressure over so I can show you how to convert these things. So pressure equals 890. Oh, not 890. What am I thinking? Pressure is 750 mmHg. Oh my goodness. Let's start with pressure first. So we got to convert it to ATM. So 1 ATM is 760 mmHg. Okay, so essentially it's going to be 750 over 760 ATM, whatever that is. I don't have my calculator with me, so I'm not doing it. Volume, it's 1 liter is every 1,000 milliliters. So 890 divided by 1,000 is 0.89 liters. And then 21 degrees Celsius, just add 273. So you get 294. Okay, and then R is that 0.0821. Okay, so we're solving for moles. So you can solve for moles before you plug in the numbers or after you plug in the numbers. If you do it before, you just have to divide by RT. Divide by RT, so you get N equals PV over RT. And then you're essentially just plugging in the numbers. So pressure was 750 over 760. Volume is 0.89. R is 0.0821. And T is 294. Okay. You notice I don't really have enough room here to do all the work. So when you do the work here, I highly encourage you to give yourself some more space. You might want to also just write it on a separate sheet of paper. Okay. For number 22, you have 1.09 grams of H2. So you got to convert that to moles. So convert to moles. Okay. For 24, STP. So temperature is 273. Pressure is 1 atm. So keep that in mind. Okay, just pointing out a couple of things there. Okay, so let's look at Dalton's law of partial pressure. So a container holds 3 gases. The partial pressures of the 3 gases are 2, 3, and 4. So you just add them all up. 2 plus 3 plus 4, 9. The pressure of oxygen plus the pressure of CO2 plus the pressure of 8 helium equals the total pressure. Okay. Graham's law. This one's a little bit tricky. So helium and argon we're looking at. Allowed to escape. Which one will get faster and how much faster? So first of all, I know helium's going to be faster because it's smaller. Okay. I actually forget what the molar mass of argon is, but it's going to be the rate of helium over the rate of argon equals the square root of the molar mass of argon over the square root of the molar mass. Sorry, my molar mass symbol was really bad there. Molar mass of helium. So just notice that they're switched. Again, it should be like a fancy M. Sure, whatever. Molar mass. Okay. All right, I'm just going to stop there. Try these as best you can, and then we'll see how you do. And we're definitely going to practice more, so don't get too discouraged if you don't get it this first time around, okay?